So we want to look at a really important result for properties of the determinant function. This one is a really useful property sometimes. It's a culmination of many things here. And we're going to just call it the title, Determinant is Multiplicative. The determinant is multiplicative. That's the way I'll entitle it. So we looked at the determinant being multiplicative when you have an elementary matrix times another matrix. It turns out, though, that the determinant is multiplicative for every pair of n by n matrices, A and B. So let's just state it this way. If A and B are n by n matrices, then the determinant of A times B, the product of A and B, you can basically pull these apart into two determinants. The determinant of A times the determinant of B. So in this video, we want to prove that. To prove that, we have to look at a preliminary. Now this was a result that we had on a previous homework. So maybe if you remember not too far back in section 2.3, page 117, number 27, you were asked to show this result in your homework. So I'm going to just state that result and write down the statement. It said if A times B is invertible, then A is invertible. Then so is A. We'll put it that way. So if you were to rewrite this statement in its contrapositive form, this is equivalent to saying if A is singular, then so is AB. So if A is singular, then AB is singular as well. Okay, so this is an important result that we're going to be using today. So let's get started with our actual proof, proving that the determinant of AB is determinant of A times determinant of B. So here it goes. We'll start with writing in blue proof. So let's suppose A and B are square matrices, n by n, are n by n matrices. And there are two possible outcomes with A. Let's just focus on A right now. Either A is invertible or A is singular. Either A is invertible or singular, one or the other. Invertible or not invertible. So there are two possible cases to consider. Let's consider the first case, case one. Let's suppose it happens that A is an invertible matrix. Suppose A is invertible. If that happens, we know by the invertible matrix theorem, then A is row equivalent. It row reduces to the n by n identity matrix. So that means there is a sequence of elementary matrices. There is a sequence of elementary matrices. And these are going to represent row operations on A. Elementary matrices. Let's call them E1, E2, and so on and so forth, all the way to EK. Such that E1, E2, and so on and so forth. EK, when these elementary matrices operate on A, it's going to give you the identity, right? It turns A into the identity. Now, what we want to do next is multiply by the inverse of each elementary matrix. So we know elementary matrices are invertible, so we're going to multiply on the left by EK inverse, and that's going to get rid of EK, and then on the left by EK minus 1 inverse, EK minus 2 inverse, and you keep going. So we're going to have A eventually by itself equals, you're going to multiply EK inverse first. That'd be the first one you multiply on the left, and then you would multiply EK minus 1 and so on and so forth. E2 inverse would be the next to the last, and the very last thing you would have to get rid of would be E1, so you multiply by E1 inverse on the left. So in other words, A is going to be what? E1 inverse, E2 inverse, EK inverse. And remember that these are actually elementary matrices themselves, right? Inverses of elementary matrices are elementary matrices. It turns out that A is a product of elementary matrices. So now let's take the determinant of AB. So in place of A, I can put these elementary matrices, E1 inverse, E2 inverse, so on and so forth, EK inverse, and I'll just keep B as it is. So we have a bunch of elementary matrices that are multiplying on the left by B. Now we know that elementary matrices, when multiplied on the left by other matrices, are multiplicative, so we can peel off the determinant of each of these elementary matrices one at a time. So first peel off the determinant of E1 inverse. And then from there you can peel off the determinant of E2 inverse, and so on and so forth. So we're using this multiplicative property for elementary matrices when they're on the left of another matrix. Then in the end, we're going to have determinant of B at the very end of all this. Okay, let's scroll. Now, those determinants of those elementary matrices, we can actually use the multiplicative property again for elementary matrices, and we can put them back together into one matrix. Let's say E1 inverse, E2 inverse, EK inverse. So you can put them back together because we have the multiplicative property for elementary matrices. And remember what this matrix is. What is this matrix? E1 inverse, E2 inverse, through EK inverse. That was A, right? That was A. Remember A here? It was this guy. This is just A right here. So we have determinant of A times, here's the determinant of B. Okay, so we've proven that determinant of AB is equal to determinant of A times determinant of B. That's when A is invertible. So we've proven one case where A is invertible. So the other case is looking at when A is singular. What happens when A is singular? Well, actually, this case is easier. I left that easiest for last, so let's see what happens. Case 2. Suppose instead that A is a singular matrix. So there's a really nice theorem that says determinants of invertible matrices are not zero. So what about determinants of singular matrices? Well, they would be equal to zero. So then that means determinant of A is equal to zero. Now, at the very beginning of this lesson, we gave you something very important. Let's go back to the very beginning before we started our proof. Remember, if A is singular, then so is AB. So here, in case 2, we have A is singular. So we're going to use that fact that we stated earlier. So note also AB is singular. Note also AB is singular. So what do we know about the determinant of AB? Well, AB is singular. That means then the determinant of AB must be 0 as well. So here we go. So what do we have? We have determinant of AB is 0, right? And 0 is going to be what? The same thing as 0 times determinant of B, right? 0 times determinant of B is 0. But wait a second. What is another name for 0 here? Well, 0 is the same thing as the determinant of A in this case. So I can replace this 0 with determinant of A. So I end up with determinant of AB equals determinant of A times determinant of B. So this is the second case proven. So this proves it in general, that determinant of AB is determinant of A times determinant of B. So we did the first invertible case and then the singular case just for A. Yeah, we don't have to even worry about whether B is invertible or not.